Deep learning models are designed to achieve a fundamental objective: accurately predict outcomes based on complex data. These sophisticated algorithms power everything from image recognition to natural language processing. Their success hinges on their ability to learn intricate patterns. However, the journey to building highly accurate models is fraught with critical pitfalls. Two of the most significant challenges that deep learning practitioners face are overfitting and underfitting. These issues can severely undermine a model's effectiveness. Understanding these concepts is not merely academic, it is crucial for practical application. Mastering the nuances of overfitting and underfitting is essential for building robust, reliable, and generalizable deep learning models that perform well in real-world scenarios. Underfitting occurs when a deep learning model is too simplistic to capture the underlying patterns within the training data. It essentially fails to learn enough from the information provided. The model cannot adequately represent the complexity of the relationship between inputs and outputs. A model suffering from underfitting exhibits poor performance characteristics across the board. It performs poorly on the training data itself, indicating it hasn't even learned the examples it was shown. Consequently, its performance on unseen test data is also predictably poor. This phenomenon is often characterized by high bias. A high bias model makes strong, incorrect assumptions about the data, leading it to consistently miss the relevant relationships. It oversimplifies the problem, failing to account for the true data distribution. Several common causes contribute to underfitting. One primary reason is using an overly simple model architecture for a complex problem. For instance, attempting to fit a linear model to inherently nonlinear data will almost certainly result in underfitting. Insufficient training data can also lead to underfitting, as the model lacks enough examples to discern meaningful patterns. Similarly, training a model for too few epochs means it hasn't had enough iterations to converge and learn effectively. The learning process is cut short before the model can grasp the data structure. The core concept behind underfitting is straightforward: the model has not learned enough. It is like a student who hasn't studied sufficiently for an exam and therefore performs poorly on all questions, both familiar and unfamiliar. In contrast to underfitting, overfitting occurs when a deep learning model learns the training data too well. It becomes excessively specialized to the specific examples it was trained on. This includes memorizing noise and irrelevant details present in the training set. An overfit model exhibits excellent performance on the training data, often achieving near-perfect accuracy. However, this impressive training performance does not translate to new, unseen data. Its performance on a test set is typically poor, sometimes drastically so. This behavior is a manifestation of high variance. A high variance model is overly sensitive to the specific training data points. It captures random fluctuations and idiosyncrasies rather than the true underlying signal, making it unstable when presented with new data. Common causes of overfitting include using an overly complex model architecture. A very deep neural network with many parameters can easily memorize the training data rather than generalize from it. Such a model has too much capacity for the given problem. Insufficient training data can also contribute to overfitting, as the model has too few examples to learn generalizable patterns. With limited data, it's easier for a complex model to simply memorize the available instances. Training for too many epochs is another frequent cause. When a model is trained for an excessive number of iterations, it starts to learn the noise in the training data. It moves beyond capturing general trends and begins to fit the specific random errors. The core concept here is that the model memorizes instead of generalizes. Distinguishing between overfitting and underfitting is crucial for effective model development. The key lies in observing the model's performance on both its training data and a separate, unseen test data set. These two scenarios present distinct performance profiles. An underfit model struggles significantly with both training and testing data. Its error rates will be high on the training set, indicating it hasn't learned the basic relationships. Consequently, its error rates on the test set will also be high, confirming its inability to generalize. Conversely, an overfit model excels on the training data, often showing very low error rates or high accuracy. This strong performance on familiar data is deceptive. When presented with the test data, its performance drops considerably, revealing its failure to generalize to new examples. The divergence in performance between training and test sets is the hallmark of overfitting. A large gap suggests the model has memorized rather than learned. For underfitting, the poor performance is consistent across both datasets. Understanding this distinction allows practitioners to diagnose the problem correctly. Without this insight, attempts to improve the model might exacerbate the existing issue rather than resolve it. It guides the selection of appropriate mitigation strategies. The ultimate goal in deep learning is to achieve optimal generalization. This means developing a model that performs exceptionally well not just on the training data, but also on new, unseen data. This sweet spot balances complexity and simplicity. Achieving this balance requires a strategic approach, employing various techniques to prevent both underfitting and overfitting. These strategies aim to guide the model towards learning robust, transferable patterns. They ensure the model is neither too simple nor too complex. One powerful strategy is data augmentation. This technique artificially increases the size and diversity of the training data. It involves creating modified versions of existing examples, such as rotating, flipping, or cropping images. Data augmentation helps prevent overfitting by exposing the model to a wider range of variations. This makes the model more robust and less likely to memorize specific training examples. It effectively expands the dataset without collecting new raw data. Regularization techniques are another cornerstone for preventing overfitting. Methods like L1 and L2 regularization add a penalty term to the loss function. This penalty discourages the model from assigning excessively large weights to features. By penalizing complex models, regularization encourages simpler solutions that are less prone to memorizing noise. L1 regularization can lead to sparse models by driving some weights to zero, effectively performing feature selection. L2 regularization, also known as weight decay, shrinks weights towards zero, promoting smaller, more distributed weights. Dropout is a widely used regularization technique specific to neural networks. During training, dropout randomly deactivates a fraction of neurons at each update step. This means that different subsets of neurons are active for different training examples. This random deactivation prevents the network from relying too heavily on any single neuron or specific set of neurons. It forces the network to learn more robust features, as each neuron must be able to perform well even if its neighbors are dropped. Dropout effectively trains an ensemble of many different networks. Early stopping is a practical and effective strategy to prevent overfitting. It involves monitoring the model's performance on a separate validation set during training. The training process is halted when the performance on this validation set begins to degrade. This degradation typically indicates that the model has started to overfit the training data. Early stopping ensures that the model is saved at its optimal generalization point before it begins to memorize noise. It prevents unnecessary training iterations. Finally, cross-validation is a robust technique for evaluating model performance and estimating its generalization ability. Instead of a single train test split, the data is divided into multiple subsets or folds. The model is then trained and evaluated multiple times. In k-fold cross-validation, the data is split into k-folds. The model is trained on k1 folds and validated on the remaining fold, repeating this process k times. This provides a more reliable estimate of the model's performance and helps in hyperparameter tuning. Cross-validation helps in understanding how well the model generalizes across different subsets of the data. It reduces the risk of a single, arbitrary train test split leading to misleading performance estimates. It is crucial for robust model assessment. Understanding the nuances of overfitting and underfitting is paramount for anyone working with deep learning models. These two phenomena represent fundamental challenges in model development, directly impacting a model's real-world utility. Recognizing their distinct characteristics is the first step toward building effective solutions. It is equally important to actively employ the various techniques designed to mitigate these issues. Strategies such as data augmentation, regularization, dropout, early stopping, and cross-validation are not optional additions. They are integral components of a robust deep learning workflow. These methods collectively guide the model towards optimal learning. By diligently applying these strategies, practitioners can steer their models away from the pitfalls of being too simplistic or too complex. The ultimate outcome is the creation of accurate, reliable, and generalizable models. These models can then perform consistently well on unseen data, fulfilling their predictive purpose. Achieving this balance between underfitting and overfitting is an essential balancing act for real-world deep learning success. It transforms a theoretical understanding into practical, high-performing applications. Mastering this equilibrium is a hallmark of skilled deep learning engineering.